Okay. What about problem statement? Problem statement, let's look at the core problem driving the study. In current educational settings, ICT instruction relies too heavily on theory. This creates a gap where abstract concepts remain detached from physical practice, where students only see code on a screen and their algorithmic thinking skills lack real development. Furthermore, we have observed the traditional coding methods often decrease learner interest because they feel disconnected from the real world, unfortunately. The most critical issue here is that students become more consumers of technology rather than active procedures. We want to change this narrative by moving from the abstract to the tangible. And what about introduction and framework? Now, let's explore the introduction and the theoretical framework of our study. Our pedagogical approach is deeply grounded in the constructivist learning paradigm. Specifically, utilizing the paper's constructionism, we believe that learning happens most effectively when and students actively make tangible objects in the study and the robotic behaviors externalized internal student logic. When students write code and see physical robot move and their abstract thinking becomes visible. Therefore, this interactive making bridges theoretical knowledge gaps immediately. Ultimately, this physical interaction empowers deep cognitive growth and helps secondary school students master complex computational structures through trial and error. How about my research purpose? Uh, Moving on the core purpose of our study, the main objective of this research is to investigate how physical computing affects student development in secondary education. To achieve this, we focus on three main research questions. First, we examine how hardware prototyping impacts students' technical competence. Second, we analyze how troubleshooting process improve their coding logic. And finally, we look at the overall effects of these robotics activities on intrinsic motivation. Essentially, we want to measure both the technical and the pedagogical growth of our learners. What about my methodology? Firstly, we'll look up the methodology as research design. Now, let's look at the methodology and research design of our study to deeply understand how students interact with physical computing. We adopted a process-oriented qualitative research design. Our study group consisted of 7 grade students. Basically, not only 7 grade students, from fifth and the eighth grade students engaged in target ICT activities. Over the course of the implementation, data was collected through interactive hardware prototyping observation cycles. We closely monitored how students translated their abstract logic formulation into concrete physical execution using open source and microcontrollers and various sensor networks. This qualitative hands-on tracking allows us to analyze the real-time problem-solving behaviors directly in the classroom environment. And the art section of this methodology, participations, and tools. And the study was carried out with secondary school students who were actively following our standard ICT curriculum. Structurally, and the environment was designed as an iterative hardware design environment to promote open-ended experimentation. For our physical computing tools, we utilized the programmable microcontroller prototyping boards as the main processing units, such as Arduino and microbit components. To drive and physical feedback, we embedded diverse sensor and actuator networks, allowing to interact with the real world. Rather than following rigid recipes, students were given open-ended educational robotics tasks which actually triggered continuous cycle of circuit manipulation, especially logical adjustments and the autonomous hardware debugging. And the last section of the data analysis, the methodology, to maintain high academic rigor, the quantitative data gathered from our observation cycles was analyzed using the thematic analysis. We follow the systematic process of open coding to identify recurring patterns in student behaviors. And these initial codes were then grouped into sub-themes. And these were generally carefully refined from our main descriptive themes to ensure the validity and reliability of our findings. We applied investigator triangulation throughout the analytic process. This structured approach allowed us to transform qualitative classroom observations into well-defined object insights regarding student progress. And the section of this study was very important for us. And what about the findings? When we talk about the findings, uh, sorry, technical proficiency is very important. Starting with technical proficiency, and our analysis revealed a very high mastery in student technical competencies. As you can see on the chart, hardware prototyping and circuit design skills reached a robust 85%. When it came to the code logic and the formulation, students demonstrated a 78% success rate. So we can mean that students really want to thinkable products. Most striking result was in troubleshooting capabilities. It is very important in programming, which peaked at 92%. This significant increase proves that learning from error cycles directly improve autonomous debugging. Lastly, the spatial reasoning and the adaptive problem-solving capabilities rose to 70%. Overall, these findings clearly demonstrate that physical computing bridges the gap between abstract code and the constrained technical mystery. And what about findings at the scope of pedagogical impact? Pedagogy impact is really important, and beyond technological proficiency, our qualitative data clearly demonstrate a profound transformation in student attitudes. First, we observed that intrinsic motivation increased substantially because the students were creating physical artifacts. Their engagement was driven by curiosity and rather than external grades. And they produce something new on their own. And the second, and the self-directed learning skills improved significantly when faced with design challenges. Students autonomously searched for solutions. Furthermore, STEM engagement levels rose, breaking down negative stereotypes about engineering. We also noted that spatial reasoning capabilities trained through the three-dimensional circuit layout manipulation. Ultimately, these results confirm that uh, physical physical computing creates a supportive ecosystem for adaptive problem-solving development. Look at this chart here at the screen at the right side of the screen. There are about some issues, their findings about technical proficiency, hardware prototyping, troubleshooting skills, logic formulation, and technical competence. And then uh, we mentioned pedagogical impact about findings. And what about conclusion, suggestion, and reference? If you wonder to conclude our study process that the learning by doing. I want to say it again: learning by doing. Brain work successfully bridge the gaps between abstract code and the tangible reality. Significantly, the boosting technical mastery and the student motivation. On this, we took three actions. First, we made open-ended robotics international ICT curriculum. Second, they provide troubleshooting guides for teachers. And third, prioritize affordable open source hardware to ensure accessibility. And our academic foundation relates 1K literature by generally papered, Resnick, and Wing as in our references. Thank you very much for your time and participation. I'm now ready for your questions.